Welcome back to the Math Professors. Our YouTube channel covers topics that can be found in any college math class. So today what I want to cover is vector fields and work. So if you like the free content, please consider liking, subscribing, and sharing to help us grow our channel. So vector fields. In order to do work, I have to discuss vector fields first, and I want to get a good feel for this. So a vector field on a domain assigns a vector to each point on the domain. A vector field of 3 dimensions looks like this. So f of x comma y is going to be equal to m of x comma y I, n of x comma y z, j plus p of x comma y z k. So you can see that each one of these component vectors are of x comma y comma z. Now in 2 dimensions, you're going to see that it's going to be m of x comma y I plus n of x comma y just j. So you can see that this is only going to be 2 components, where each one of these components are 2-dimensional. So these vector fields are continuous if the component functions are continuous. So these are some ways to look at some vector fields, and they're going to help us describe these, work for us. All right, so to get a good feel, I want to graph some pretty simple looking vector fields, so then we can kind of take a look of like, what work can be done on that vector field on top of a curve. So let's draw some. So we're going to do the radial field first. So we're going to do this in 2 dimensions. F of x comma y is going to be equal to xi plus yj. So you can see the components are just x and y respectively. And what it says is that a vector field defines vectors for every point on this particular domain. I'm not going to do every single point because it's infinite. So we're just going to pick some integer values. So let's say 1 and 2, 1 and 2, 1 and 2. So I'm not going to do every single one of these points, but I will do a couple of them so we can get a feel for these, and then we can graph the ones between, probably by checking out the pattern that we're going to see. So if you do like a vector field, like a differential equation class, you still have to do this kind of work as well. It's quite tedious, but like I said, we will do some of these, and then we'll kind of look at pattern from there. So let's go ahead and find, say, this point right here. Let's go 2 comma 1, for instance. And I want to find that vector, what vector is at that 2 comma 1. So let's do the work over here. So f of 2 comma 1 means x is 2 and y is 1. So in this case, x is this and then y is this. So this is going to be 2i plus y is going to be 1j. And if I put these things in, I'm going to graph them in standard form. And then we will move them to, because remember, a vector can be moved in any spot in space. So in standard form, this is going to go, over 2, up 1, so it's going to look like this. Now I'm going to take the tail of that vector and put that right on this dot, so it's going to look like this. Now let's do say this point right here. What about at 0 comma 1? Well, f of 0 comma 1 would be equal to, remember, x and y. So in this case, x is going to be the variable in front of I, so 0i, and y is the variable in front of j, so plus 1j. So if I put this in standard form, 0i, 1j is just going to go up 1, the unit vector up 1, so you can see that this looks like so. How about down here at maybe 1 comma negative 1? So f of 1 comma negative 1 is going to, remember, this is x, and x is the coefficient from I, so this is 1i, and then negative 1j, so minus 1j. So in standard form, I'm going to go, positive 1 the x, negative 1 the y. So it's going to look like this, so right here. Now, as we get more and more pattern, let's say maybe this spot here will be our last one, and then I'll kind of fill in the rest of them. So what about, say, f of, this is going to be minus 2 comma 0, so x is going to be equal to negative 2i plus 0j. Standard form is going to be, over 2, nothing, then up nothing, so we're going to be here over 2. So this is going to be our vector, and that means it's going to look like this. Now we say this is a radial vector field because if we continue to draw these things, their lengths, of course, are going to be, whatever the square root of x squared plus, y squared is. So they're not going to share the same length. So as, x and y get bigger, these things are going to get larger. So this would look like this. So what this is looking like is basically like an explosion. You know, everything is going out, you know, as like rays. Okay, that's good. So you can see that that's our vector field right here. Now the next one I want to do is a one that has a little bit of a circulation. So let me pause this. I'll do one more. So here's the next one. You're going to see that this will have a little bit of a spin to it, essentially. Now I've written this as a function over a common denominator, but really if we want to write this in terms of you know, mi plus nj, it really would be your m function is going to be this I plus the n function, which is going to be x over the square root of x squared plus y squared j. But a lot of times we write them in simplified versions because that's how, you know, vectors work. So let's find some values. So again, we're going to have some vector field here, and I'm going to have to do this at, you know, all these particular numbers. So let's start out with some. How about like this? How about the same spot? 2 comma 1. So f of 2 comma 1 is going to be equal to. Remember, this is your x and this is your y. So x is here and y is here this time. So this is going to be minus 1. Actually, we'll do here. Minus 1 all over the square root of x squared plus y squared, so 2 squared plus 1 squared. I, and then plus x, which is going to be 2 over the square root of 2 squared plus 1 squared. J. So we're going to have negative 1 over root 3i plus 2 over root 3j. And if you remember your work in vectors, when you see x squared plus y squared on the bottom for these particular components, I'm really just making unit vectors here. So this is going to have the direction of, if I was going to do this in standard form, let's do it over here. So standard form, this is going to have negative 1 in the x and then 2 in the y. But it's going to have unit vectors, so it's going to be about that long. So right here it looks like this, but it has unit vector. Now let's try here. How about this one? What about that? 1 comma 0. Well, f of 1 comma 0 is going to be equal to, remember this again, this is x, this is y, so that's what we're plugging into this, or this. So this is going to be minus 0 over the square root of 1 squared plus 0 squared I, plus x is going to be 1 over the square root of 1 squared plus 0 squared j. So this is going to be 0i plus 1j simplified. So in standard form, this is only going to go in the unit vector up. So let's pick this point right here. So that's going to be 0 comma 2. So f of 0 comma 2. So again, this is x, this is y. So plug it into here. This is going to be minus 2 over the square root of 0 squared plus 2 squared I, plus x is going to be 0 over the square root of 0 squared plus 2 squared j. So simplifying this is going to be equal to minus 2 over the square root of 4, which is going to be 2. So this minus 2 over 2 is going to be minus 1i plus 0j. Really verifying that every one of these things are unit vector length, except this just goes in the x direction. And as we fill these things out for all these, you'll remember all these dots, we're going to see that we're going to get these, it looks like it's spinning. Now you can see that circulation that we're getting here. So let's describe what work is done on these particular vector fields over top of a curve. So here's a definition. Work done by a force over a curve in space. So let's suppose that we have a force of x comma y comma z, which is mi plus nj plus pk. Represents a force throughout the region, and that the curve r of t is going to be g of ti plus h of tj plus k of tk from a to b is a smooth curve in that region. Then the integral of f dot t over the curve is the work done by f over the curve from a to b. So this is the work done. The work is going to be the integral of the curve of f dot t ds. Now let me explain really, what this thing means. So what I've drawn here is a force field defined by f, and then the green curve is going to be our c. And what does f dot t technically represent? Well, this is the dot product between f and t really is the dot product between f and the unit tangent vector of RC. So what you're going to do is it's going to give us the component. Make sure I say this right. It is it's the scalar component of f in the unit tangent vector of r. So let me show you graphically. It makes a lot more sense this way. So if I put like a particle on this green curve, we kind of think the green curve as like some train tracks, and really kind of think of this force field as kind of wind. Now if I put like something here on the train tracks, we can see that the wind is going to push that thing a little bit to the right, but in the beginning I can see that this, the wind is not really going with the track, so it's only going to have a little bit of push in this direction because that particular field, this particular field is only going to have a little bit of direction in the direction of the curve. And similar here, just a little bit. And now you can see as I keep moving through this curve, we might get a little bit more and a little bit more. Even here, you can tell that the field is actually moving more with the curve. So its curve direction of the pink is now going to be a little bit larger. And then over here, you can see that this curve is almost going parallel to the pink field. So at this particular point, you're almost going to get the entire, pink line. So remember, these are just the really the green components of the pinks. So when you decompose like a triangle, if you're looking at it like this, so if I have a vector field here, well, this would be considered its x component. This would be considered its y component. But I'm not doing the x component and the y component. I'm actually doing the green component of the pink. All right, so this is not super helpful for us because I can't integrate with respect to ds. So what I need to do is I need to turn this into more of a functional integral. So let me show you how that's done. All right, so I put a little bit of work up here. We remember that the unit tangent vector is v over the magnitude of v, so I can write this as 1 over the magnitude of v times v. And also know that s is going to be the accumulation of the magnitude of v of tau d tau. So this is going to be the integral from a to t of the magnitude of v of tau d tau. So that means the derivative with respect to t is going to be the derivative with respect to t of this. And using the fundamental theorem of calculus, the derivative with respect to t is going to really cancel this integral, and this t is going to go in this location. So this becomes ds dt is going to be equal to the magnitude of v of t. So what we know is that this is going to be equal to 1 over ds dt. And we know that the magnitude, that v is dr ds. So multiplying by the reciprocal, this is going to be, dt, dr dt. And so dt over ds is going to be equal to, sorry, I meant to say v is equal to dr dt. So this is going to be equal to, get this yet. So dt over ds multiplying by the reciprocal is going to be the same thing as dr over dt. We can see that the dt's go away, so this is the same thing as dr over ds. Woo! Okay, so what we have here is this thing ends up being the integral over the curve from f dot dr ds, which ends up being the integral over the curve of f just dot dr. Now, again, still not quite useful, but daggone it, we're close. So in order to do this, we want really to integrate with respect to t just like we did with line integrals. So I can replace this with the integral from a to b of f evaluated at the curve dot dr dt dt. So this is going to be our, functional work antiderivative. We're going to use this in order to evaluate the work integral. So let's do an example or two, and that'll be it. All right, so what I want to write is different forms of the work integral. We know by definition it's the integral over c of f dot t ds. So this is the definition, which also this is the definition, not super useful, but at least it explains what it does. Now how we calculate it is going to be the integral from a to b of f, the field evaluated at the curve, dotted with the derivative of the curve with respect to t, and this integral is going to be with respect to t. Now, this thing also is considered like a differential equation of this, and you'll see that these two things really are exactly the same thing. That this says do the dot product, and that's exactly what this thing really is the dot product of f, which is m, n, and p, with the derivative of the curve, which is going to be dx, dy, dz, and you'll see that in a second here. So I'd like to do this way, and then if I have a little bit of room, I'll find some room for it. I'd like to kind of show you that this is equivalent to this. Okay, so in our example, I want to find the work done by this force field over this particular curve. Now, in order to do that, we know that we're going to have to, I'm going to have to define the force function at the curve. So I'm going to have to define this thing at this curve. So just like we did before with the line integral, we're going to have to evaluate this at the curve. So, f evaluated at r of t, which is going to be f of, x comma y comma z, plug in, this is going to be your x, this is going to be your y, this is going to be z. So really this is that field evaluated at t comma t squared comma t cubed. So that's what we mean by the field evaluated at the curve. So now we plug it in. So this is going to be equal to y, which is going to be equal to t squared. So this is t squared minus x, which is going to be t squared. So t squared, that's going to be our I. Plus now here I have z, which is going to be t cubed, minus y squared. Y is t squared, so t squared squared is going to be t to the fourth j, plus x, which is going to be equal to t, minus z squared, so t cubed squared is going to be t to the sixth, and that's going to be k. So that's the force over defined at the function, or the curve. Now I have to, I'm going to have to dot product this with dr dt, so I'm going to have to find the derivative of r of t. So dr dt is going to be, well, the derivative of this. The derivative of t is going to be, 1i plus 2tj plus t cubed k. Now I have to take the dot product. So now I'm going to need, f dot dr dt. So f is going to be this function. So when I dot these two functions, you have to multiply. We have to multiply their components and then add them up. So I didn't say that very well. So it's going to be the multiplication of the addition of the multiplication of the corresponding component. So first we're going to multiply the first components together. So this is going to be, this was just 0, right? So this is going to be 0 times 1 plus, multiply the second components together. This is going to be t cubed minus t to the fourth times 2t. Addition, multiply the third components together. This is going to be t minus t to the sixth times t cubed. And when we simplify this, this is going to be equal to, well, that's 0, distributing. So this is going to be 2t to the fourth minus 2t to the fifth. Distributing here, this is going to be plus t to the, let me pause this, make sure I got this right. I don't have this right. The reason why this is wrong is this is not 3t squared. I have to have its derivative. This is 3t squared. I knew I had an error somewhere. So this is going to be 3t squared. So multiplying this through, 3t squared times t is going to be equal to 3t cubed. 3t squared times this is going to be minus 3t to the eighth. All right. Holy cow, we're almost done. So now I have f dot dr. I have to now integrate this thing from a to b, and it says that it's a and b are going to be 0 and 1 respectively. So now we are going to integrate this from 0 to 1 of f dot dr. So this is going to be 2t to the fourth minus 2t to the fifth plus 3t cubed minus 3t to the eighth dt. So this is going to be, the antiderivative is 2t to the fifth over 5 plus, not plus, but minus 2t to the sixth over 6 plus 3t to the fourth over 4 minus 3t to the ninth over 9, evaluated from 0 to 1. And to save you the time, plug in 1, plug in 0. You can see it's just going to be these coefficients. So adding those coefficients together is going to give me 29 over 60 when we're done. Okay, so since I have some space over here, I really want to verify that this is really the exact same equation as this. So in order to do that, I'm going to have to figure out what m, n, and p are. Now when we do m, n, and p, we actually know that m is going to be equal to, so let's just box this off over here so I can show you the work. So m is going to be, it's the coefficient, the x coefficient, x component function. So this is going to be y minus x squared. So it's an I component function. N is going to be equal to this component function, so z minus y squared. And then finally p is going to be the last component function, so this is going to be x minus z squared. Now what we know we have to do is we have to evaluate this at the curve. So what we do know is our curve, x is going to be equal to t, y is going to be equal to t squared, and then finally z is going to be equal to t cubed. So evaluating these things at the components, m is going to be equal to y, which was t squared minus x squared, which is t squared. So again, m is equal to 0, just like we had here. M was equal to 0. N is going to be equal to z, which is t cubed minus y squared. So t squared squared is t to the fourth, which again is exactly what we had right here. And then z is going to be equal, p is going to be equal to x, which was t minus z squared, which is going to be t cubed squared, or t to the sixth, which is exactly what we have here. So you can see that these are the same three values, where really it's just the force evaluated at the curve. Now I'm also going to have to find dr dt. Well, one way to look at that is I need the derivative of the curve. So really your dr dt, or technically your dr to be more accurate, your dr is going to be, for this is going to be dx is going to be here. So doing the x, y, and z and taking the differentials, this is going to be dt. The differential of y, dy, is going to be equal to 2t dt. And then finally dz is going to be equal to 3t squared dt. And we can see we had the exact same things when we were finding dr dt, that I got 1 dt, I got 2t dt, and then I got 3t squared dt. So when we set this up, this really is this. So when we set this up, this is going to be the integral from 0 to 1 of m0 times dt plus n, which is going to be t cubed minus t to the fourth times 2t dt. And then finally p, which is going to be t minus t to the sixth times 3t squared dt. Now since all these things have a dt, I can just cancel this out. 0 plus t cubed minus t to the fourth times 2t plus t minus t to the sixth. I should have multiplied those, but whatever, times 3t squared all dt. And when you multiply those things out, you're going to get exactly this. So you'll see that you're going to have the integral from 0 to 1. Do I have room down here? Just barely. So this would be the integral from 0 to 1 of exactly this thing, of 2t to the fourth minus 2t to the fifth plus 3t cubed minus 3t to the eighth dt. So we resolve exactly the same integral. So therefore you're going to get 29 over 60. So again, if you like the content and want to help us grow our channel, please consider liking, subscribing, and sharing. Thank you.